Okay, let's unpack this. I want you to just imagine a scenario for a second. It's the kind of thing that gives industrial operations managers, nightmares.
Oh, yeah.
You're running a massive operation, a huge mine maybe, or a power plant, and then bang! Your biggest, most critical rotating part just fails.
Let's say a huge conveyor roller journal.
Exactly. Something supporting thousands of tons of material. It just grinds to a halt, and everything stops.
And the clock starts ticking, like immediately, the second that shaft stops turning. This isn't just about a broken part. Your asset utilization just hit zero. Every minute that conveyor isn't moving, the financial hit is it's staggering. You could be talking tens of thousands of dollars. Millions even, over a week.
All because of one worn-out groove on a big piece of metal.
Yeah.
And the old way of dealing with this, the standard reaction, it was a logistical nightmare.
Oh, a total disaster in motion. So much risk, so much inefficiency.
So break that down. What did that old way actually look like?
Okay, so step one, safety teams have to come in, cordon everything off. Step two, you get specialized heavy riggers to bring in like a 40-ton crane.
Just to lift the component out.
Just to delicately lift this enormous, probably filthy roller out of its housing. Then you've got to load it onto a specialty truck and send it maybe hundreds of miles away to the one machine shop that can even handle it.
And then you just wait. It goes into a queue.
Precisely.
Yeah.
It's in line behind a dozen other emergencies. The shop trips it, machines it, ships it back. I mean, you're not talking hours. You're not even talking days. You're talking weeks.
Weeks of paralysis.
Yeah, weeks. And all the safety risks that come with moving something that heavy that many times, it was just unsustainable.
And this is where it gets really interesting for our deep dive today, because that entire process, that whole weeks-long nightmare, it's been basically neutralized by portable machining.
The game completely changed.
So our mission today is to really get into the tech that brought the machine shop to the job site, the portable shaft lathe. This thing cuts that repair time from weeks down to, what, hours or maybe a day or two?
Right. By doing the high-precision repair right there, on site, in the middle of all the dust and the heat.
So we need to unpack how it works, what makes it so tough, and how in the world it delivers workshop-level precision when it's just bolted onto a damaged shaft.
And which industries really just can't function without it anymore.
Okay, so let's start with the absolute basics. What is a portable shaft lathe? It's not just a big hand tool, right? It's more like a whole machine shop, but shrunk down.
That's a perfect way to think about it. It's a compact, really heavy-duty machine tool made specifically for on-site turning.
Okay.
But the key difference, the thing that changes everything, is how it mounts. Instead of bringing the huge shaft to the machine...
You bring the machine to the shaft?
Exactly. It mounts directly to the component.
It just clamps right on with bolts or something.
That's right. It uses the shaft as its own anchor, its own reference point. So the machine rotates the cutting tool around the shaft, which stays put. You can turn down a worn surface without ever moving the main asset.
And that's where the time savings come from.
That's everything.
The sources we looked at also mentioned its versatility. I mean, this isn't just for a shaft lying flat on the ground.
Oh, not at all. Think about the inside of a ship's engine room or a vertical pump shaft deep in a mine. The design is modular, so you can set it up horizontally, vertically, even at an odd angle.
And they fit into really tight spots.
Incredibly space efficient. You often only need a few inches of radial clearance to get it mounted. It can get into places a traditional tool could never dream of.
What about power? I imagine out on a remote site, that's a big issue.
It is, and they're built for it. They can run off electric, hydraulic, or pneumatic power.
Oh.
So yeah, you can use them on a remote drilling rig, deep in a mine, anywhere.
Okay, so let's get to the big engineering question here. The thing that makes you skeptical.
Yeah.
You've got this compact machine, it's bolted onto this massive shaft, maybe in a vibrating, dirty environment. How do you possibly get a smooth quality finish? What's the secret sauce for stability?
That is the essential question, and it's what separates the professional-grade machines from, a rough field fix.
Yeah.
The stability is all engineered into the spindle system.
The spindle system looks good.
Specifically, they use these heavy-duty, zero-clearance spindle bearings.
Okay, break that down for us. Why is zero clearance the magic phrase here?
Well, in a normal machine shop, your stability comes from, tons of concrete and a massive, heavy machine.
Right, a stable foundation.
You don't have that in the field. Any little vibration from other equipment, from the cutting itself, it creates what's called chatter, little tiny imperfections on the surface.
Which ruins the finish.
Exactly. Zero clearance bearings eliminate any potential for play or wobble in that cutting head. It makes the connection totally rigid no matter what. That's how you get a pristine, vibration-free finish,
Yeah.
even outside a clean room.
And that rigidity means you can set it up fast. I think one source said in under an hour, which is key.
It is. If the setup takes you all day, you've lost your advantage.
Okay, let's talk about the actual damage. The machine is fast, it's stable, but can it handle the really bad stuff, the reason the line shut down in the first place?
Right. And it's important to be clear here. The sources say it is not for like huge structural cracks or failures that compromise the metal itself.
Okay, so no catastrophic failures.
No. But it's engineered perfectly for restoring surfaces. It can handle the 5 most common reasons a critical shaft will fail.
So when the repair crew shows up, what are they usually looking at?
Okay, so first you've got just general wear and abrasion, just turning down a surface damaged by friction or dirt to get a nice uniform diameter again.
Simple enough.
Second, and this is maybe the most critical one, is repairing bearing and seal seats. So resurfacing those worn journals to make sure the new bearing fits perfectly, that's vital.
To prevent it from failing again? What about connections, like on the ends of shafts?
Yeah. Third is damaged threads and keyways. They can recut stripped threads on a coupling or fix a damaged keyway that holds a gear in place.
And just general surface damage.
That's number 4. Scratches, pitting, corrosion, anything that might compromise a high-pressure seal, they can machine that away.
And the last one, I think, deals with fixing bad fixes.
You got it. Fifth is weld buildup. If a shaft had a structural repair where they added metal, it's called a weld overlay, the lathe machines that new material back down to the original precise dimensions.
That brings up a good point, though. If a shaft is really worn down and you machine off, say, another 3 millimeters, which these things can apparently do in one pass.
Which is a huge amount of material removal, yeah.
Aren't you just left with a shaft that's too small?
That's a great question. The lathe's job is just dimensional restoration, to make the surface perfectly round and true again. Once you have that perfect geometry, the engineers decide on the next step. Maybe they install a sleeve or use thermal spray to build the diameter back up for another pass, or, most often, they just specify an undersized bearing.
So the lathe does the hard part on site.
It does the hard, time-consuming part immediately. And that power, that 3 millimeter cutting depth, that's what turns days of roughing work into just a few hours.
This brings us to the biggest technical hurdle, the thing that makes managers hesitate. Can a repair done out in the field really match the precision of a climate-controlled machine shop?
Right. The skepticism is totally warranted.
But does it?
The short answer is unequivocally yes. Modern portable lathes deliver workshop-level precision, and we have the numbers to prove it.
Okay, lay them on us. What are the metrics?
We're talking about achieving dimensional tolerances as tight as 0.001 inches.
1,000th of an inch.
Yeah, which is just over 25 microns. And for surface quality, they can get a roughness rating of up to R3.2.
Okay, 1,000th of an inch is, what, less than a human hair? That's incredibly tight. But what does R3.2 mean in the real world for the person who just needs the machine to work?
That's the key part. R3.2 isn't just smooth. It's a specific engineering requirement. It's the finish you need for, say, a high-speed turbine bearing to maintain its oil film so you don't get metal-on-metal contact.
Ah, okay.
Or it's the exact roughness needed for a hydraulic seal to hold thousands of PSI without leaking. It means the repaired surface performs exactly like a brand-new OEM part. It guarantees reliability.
And how do they maintain that accuracy out there? It's more than just the bearings, I assume.
It is. The bearings are the foundation, but the whole system is built for it. They use super rigid mounting systems, and then they pair that with high-precision electronic actuators that control the tool's feed rate.
So the movement is automated and controlled?
Exactly. It's smooth, consistent, and measured in microns. You basically decouple the precision from the environment and the operator. You're not trading quality for speed.
So we've got the solution. We've proven the quality. Let's talk about who depends on this. This isn't some niche tech, right? It's critical infrastructure.
It really is. The problem is the same everywhere. The equipment is too big, too important, or just plain impossible to move. Bringing the tool to the job is the only thing that makes sense.
So give us the rundown. Where is this technology an absolute must-have?
Well, it reads like a list of the global economy's backbone. You start with mining and material handling. There are huge conveyor rollers, crushers, haul truck axles,
At least one.
and power generation, hydro, fossil fuel, nuclear plants. They all use this on their massive turbine and generator shafts.
Let's talk about ships. That seems like a perfect example of something you just can't move.
Shipbuilding and marine is a massive user, yeah.
Yeah.
Imagine a container ship damages its propeller shaft. To remove that, you need a dry dock, which can cost millions in delays.
A logistical nightmare.
But if you can machine a bearing journal while the ship is just docked for a short time, it totally changes the economics of the repair.
What about the energy sector?
Oil and gas, absolutely. Pump shafts, drilling equipment, pipeline parts that are way out in the middle of nowhere. It's the same story for heavy manufacturing with their huge motor shafts and press rollers.
The common thread is always the cost of downtime.
Always. Even in paper and pulp mills with their giant rollers or construction. The alternative, which is shipping the broken part, is always slower and way more expensive. So if we circle back to our original problem, that paralyzed mind waiting weeks for a part, the portable lathe gives you this triple benefit. It slashes downtime, it cuts logistical costs and safety risks, and it delivers high-precision results right where you need them.
The whole value proposition is just a fundamental shift in maintenance philosophy, isn't it? Moving away from a centralized, bottlenecked machine shop
to a decentralized, high-accuracy on-site solution. It just completely changes the math on how you manage your assets.
It's the difference between being down for 20 days and being back up and running in 2.
With a shaft that's repaired to 1/1000th of an inch and an R3.2 finish.
Which I think raises a really interesting final question for you, the listener, to think about. If these portable, rugged on-site machines can hit 0.001-inch tolerances, the kind of precision needed for critical seals, what's next? What other complex maintenance stuff that currently requires a trip back to the factory could soon be done by just bringing a specialized tool directly to the asset?
The world of precision engineering is clearly going mobile. And the next decade will be defined by what else we can fix without ever having to call for a crane.